Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back again to this online structural geology NPTEL course. In this week we are learning folds and folding, and we are lecture number 21, and we will learn in this lecture, this is the second lecture of this week, we will learn classifications of foldings. In the previous lecture we learned a series of terminologies to describe a folded structure or a folded layer. And these ranged from point related structures, line related structures, and also plane related structures. And these include hinge line, fold axis, inflection points, inflection line, median surfaces, enveloping surface. Then we also learned interlimb angles, we learned crest, we learned trough, we learned limb, we learned hinge zone, and so on. So there are so many terminologies we learned in our last lecture. I hope you went through this and you understood all these terminologies, their physical significance and their actual meaning. In this lecture what we will do, we will use most of these terminologies to describe a folded structure and to understand that which fold is what, and in other way, or in other words, we will be classifying the folded structures. So yes, there is only one aim in this lecture, and that is classification of folded structure. Now, as you have understood from the previous lecture, because we had to use a lot of terminologies to describe a folded geometry, so it is not very easy to quantitatively or accurately describe the geometry of a fold, and it is difficult, and at the same time it is time consuming. Also, it is not very easy to communicate the other people that yes, I have seen this kind of fold in the field, in quantitative manner of course. So most of the times what structural geologists do, they try to describe the folded structure in qualitative manner, and while doing so the structural geologists do use a combination of certain terminologies. We have learned few in the previous lecture, and in this lecture we learn a few more. And all these descriptions, these qualitative descriptions sort of provide us a rough idea of the shape of a fold, and at the same time the orientation of the structural elements which are associated with folded structure. Just for example, if I use a terminology that this is X type of fold, then a visualization appears that okay, the fold is like this. If I say no, this is Y type of fold, then another visualization appears. So in this lecture we will sort of cover all these kind of features, and we will try to again classify the features that we have learned in the previous lecture, and few of these we will learn in this lecture. So folds are commonly classified based on series of parameters, and here I listed a few which I will cover in this lecture, and these include sense of curvature of this fold or form surface of this fold. Then stratigraphic direction, we will consider that as well, that whether the fold core is representing young layers or older layers. Then folds also do have symmetry because it's some sort of sinuous. So whether the fold is symmetric or asymmetric, we will also test that. How the axial plane is oriented, that's also a parameter to classify the folds. Plunge of the fold axis, because fold axis is a linear feature, so it must have a trend and plunge, and we take the plunge to classify the folds. The curvature of hinge line and fold axis is also a major parameter, that whether the fold axis is straight or curved, and we will see how do we classify folds based on that. Then curvature of the axial plane as well. A plane not necessarily is a straight plane, it can be curved, and we will classify folded structures based on that as well. The interlimb angles, the angles can be wider or shorter. So we will also check that in classifying the folds. Then shape of the fold hinge is also an important parameter, and finally we will classify the folds based on how it is related with the neighboring structures. And while we will study all these things, I have restricted all these things to illustrations, or in other ways that I did not use in this presentation any image or photograph. You can check all these image and photographs if you would like to in your search engine. You just type the name of that fold and you will see it. So I didn't want to sort of populate or crowd this presentation, but tried to give some easily understandable illustrations to better identify and better comprehend the classification of folds. However, if requires, in the next lecture I will try to add some photographs which are very key features, where you will see some key features of a folded structure. So let's start first with the sense of curvature. And these two terms we have learned already in the previous lecture. One is antiform and another is synform, and they are given in these two illustrations. So we learned in the previous lecture, antiform is a fold that closes upward. So as you can see here, this fold is closing upward, so this is an antiform. This fold is a synform because it is closing downward. But there could be a series of possibilities where the fold is not closing upward or downward, but sidewise. In that case, we call it neutral fold, where the closure is not upward, not downward, but sidewise. We can also consider a fold something like that. This fold has a special name, we will learn it later, but as you can see, this fold is also not closing upward or downward, so this is also a kind of neutral fold. So any fold which is not closing downward or upward, you can classify them or you can group them as neutral fold that closes sidewise. Now, stratigraphic Younging direction of the fold closure. Here we have two primary terminologies to classify or to take into account the stratigraphy of the folded strata. So these two terms that those are written here, anticline and syncline, these are only restricted to the form surfaces defined by sedimentary layers, because in other form surfaces like veins or foliations and so on, these are not really included in describing anticline and synclines. So let's have their definition first, as it is written here. An anticline is a fold in which the direction of younging is away from the fold core, and a syncline is a fold in which the direction of younging is towards the fold core. Let's first look at this image. So as you can see that in the top layer, which is written here, this is younging layer, and the bottom layer is older layer. Say in the top layer you find the fossil ammonite, and in the bottom layer you find the fossil of trilobite. So therefore top layer is of Mesozoic age and the bottom layer is of Paleozoic age. Now what we see in this first fold, if I consider this one, then this is a synform, as we have learned from the previous lecture, and it is closing downwards. So this is essentially a synform. Now in this synform, the younging direction or the younger layer is towards the fold core. So this is the younging layer and this is the older layer. Now younging layer, if it is towards the fold core, then we call it syncline. But in the next wave, if we consider this one, this particular wave, what we see here that it is closing upward. So this is an antiform, and in this antiform the younging layer is away from the fold core. So this is your fold core and the younging layer is away from the fold core. Therefore we, as per definition, we term it as anticline. So syncline, anticline, syncline, anticline, this is how it progresses in a folded strata. So I repeat, synform and antiform are geometry based terminologies, and anticline and syncline are also geometry based terminologies, but they also include the stratigraphic Younging direction. So if we have a large anticline with many smaller folds, then we term it anticlinorium, and if we have a large syncline with many smaller folds, then we term it as synclinorium. So as you can see, this is a packet of folds, or we can actually make a large fold like this, right? And it is defined by many small folds, as you can see here in this illustration. Now, in all these folds, the top part is defined by the fossil ammonite, so that means this is the Younging direction. So this is a synform, and the synform contains many smaller folds, so this is a synclinorium, and in a similar way this is an antiform because it is closing upward, and Younging direction is also away from the core, so this is an anticlinorium as it is consisting of many smaller folds. So we learned syncline, anticline, and now we learned anticlinorium and synclinorium. The picture becomes little complicated when this stratigraphic Younging direction reverses, and we will see this in the next slide. The first one we will take is synformal anticline, and then we will take antiformal syncline. Now an anticline is, we learnt in the previous lecture, when the Younging direction is away from the fold core in an antiformal structure. But in this case, in an synformal anticline, a fold that closes downwards, but the direction of Younging is away from the fold core. And the reverse happens when you have antiformal syncline, a fold that closes upward, but the Younging direction is towards the fold core. The folds generally produce this kind of structures like synformal anticline or antiformal syncline. Is little complicated, but we'll understand it with this illustration given here. So you can imagine the fact that this is your Younging layer here, going here, defined by this ammonite fossil, and this is the older layer. So if I see in this section, which is little faded, so clearly this is an anticline, and the next segment, the Younging layer is at the core, older layer away from the core, and this form is a synform, so this is syncline, no problem. But if the folded strata is curved and got a turn in this side, then interestingly you see that this brighter area here, which is not faded, the Younging layer comes at the bottom of the stratigraphy and older layer is at the top of the stratigraphy. In that case, this structure is a synform because this is closing downwards, it is closing this way. The structure next to this, the folded structure, is an antiform because it is closing upward. However, we see that in this synform, the younger layer is away from the fold core. So this is an actually anticline. So therefore, we name it a synformal anticline. And similarly, in this antiform, the Younging layer is towards the fold core. So this is antiformal syncline. So we learned a series of terminologies related to fold geometry and their stratigraphic Younging directions: synform, antiform, syncline, anticline, synformal anticline, antiformal syncline, and anticlinorium and synclinorium. Let's talk about the symmetry of the fold. So you can understand this fact that a fold can be symmetric or asymmetric. A symmetric fold is if in profile section, that means a section perpendicular to the fold axis, the shape of one side of the hinge is a mirror image on the other side and the limbs are of identical length. The plane of symmetry therefore is the axial plane and is also the bisector of the median surface. An asymmetric fold is where all these conditions do not hold, or in other ways, a fold that does not have any mirror plane of symmetry and the limbs are of unequal length. Let's concentrate on these two illustrations in this slide. The first one is an illustration of a symmetric fold. As you can see here, that if I bisect the fold with this red line here, then this part of the fold and this particular part of the fold, which is also the next plane of symmetry, mirror plane of symmetry. So, this part and this part, they are very similar to each other, or they are mirror image to each other. So, therefore, this folded structure as per definition is symmetric fold. Also, the length of the limb, if I can consider from here to here or here to here, considering it has no hinge zone, then they are also similar to each other. Also, this layer, as it is mirror symmetry, if I consider this angle theta 1 and if I consider this angle as theta 2, in a symmetric fold, theta 1 should be equal to theta 2. And this plane of symmetry is the trace of the axial plane. We will learn it later that this is also axial planar cleavage. In contrary, in asymmetric fold, there is no plane of symmetry, or there is no plane of mirror image. So, you can see that if I consider this segment of this fold and this line, if I consider, or any other line, you cannot produce a mirror image of the other side. So, therefore, this fold is asymmetric. You can also see the length of this limb is longer than the length of this other limb, considering it does not have any hinge zone. This angle, if you measure, this angle is theta 1, this angle is theta 2, and in this case theta 1 is not equal to theta 2. So, this is how we define the symmetric fold and asymmetric fold. The asymmetric fold is a counterclockwise fold or an S fold if the short limb has rotated counterclockwise with respect to the long limb. Also, the short limb together with the adjacent long limbs define an S shape. Now, we now focus on this illustration. Again, if I consider that there was a symmetric fold, something like that, and then if I rotate it counterclockwise, then it may take a shape like this, where this is the short limb and this is the long limb, and the resultant structure is here. So, it rotated counterclockwise, the short limb. Also, you see that this short limb together with the adjacent two other limbs, it defines the English letter S. So, this is clockwise and this is anti-clockwise asymmetric fold. Now, in a single strata or in a single layer, we can have this clockwise or anti-clockwise folds, or in other ways we can figure out Z and S shaped fold. So, here, so with a folded structure, the Z and S folds systematically appear across the axial surface. So, in a single fold you can see them. Now, if the folds in a limb have a clockwise apparent vergence, are described as Z folds. So, let us have a look. Here you can see in this limb, particularly if you consider this one and this one. Okay. So, here you see these are Z. On the other hand, those on the other limb have anti-clockwise apparent vergence. Here, these are S shaped. Now, in between these Z and S, you may find symmetric M fold if it is an antiform, as you can see here, it is closing upward, If it is sin-form, instead of M, you may find a W type of fold. So in the field we sometimes describe this as S fold, Z fold, W fold or M fold. So if your teacher, colleague or if your friend tells you that, okay, in the field I have seen a Z fold, then now you can immediately relate what he or she is talking about. Now let's have a look how we classify the folds based on the orientation of axial planes. A number of terminologies we will be using here. The first one is upright fold with vertical or nearly vertical axial planes. The second one is recumbent fold with axial planes dipping at an angle of 10 degrees or less, or you can consider the axial plane is somehow sub-horizontal or horizontal. The inclined fold is anything in between upright and recumbent fold, that means the fold axial planes are inclined. The reclined fold is a very special type of inclined fold in which the pitch of the fold axis on the axial plane is vertical or is orthogonal, is about 80 to 100 degrees. An overturned fold is also a kind of inclined fold in which both of the limbs have the same sense of inclination. So based on the orientation of axial planes, we define folds or we classify folds as upright folds, recumbent folds, inclined folds, reclined folds and overturned folds. The definitions are given here, and now we will see them in the form of illustrations. And here they are. In all these illustrations, the blue shaped rectangles are the axial planes. What do we see in this first illustration, which is an example of upright fold? We see that this is the folded strata, folded layer, and this axial plane is this one, and the axial plane is almost vertical. In the second one, we see that this is a recumbent fold. So in the field, if you figure it out, you will write it like this, or you can orient it like this in this way. So if you have to map it, you can plot it like this, where this long line is the strike of this axial plane, and this defines that this is vertical. We learnt it in our deep strike lecture. In the recumbent fold, you see this is the folded strata, and here this is your axial plane, which is horizontal, and we call it recumbent. So in the map, you will define it something like that. Now inclined fold, we clearly see that this axial plane, this blue plane is inclined, it is dipping towards this side. So axial plane is neither vertical nor horizontal, it is inclined. Reclined fold, as I said, it is a very interesting fold where the pitch of the fold axis is almost 90 degrees, or it ranges from 80 to 100 degrees with the strike of the axial plane. So if this is the axial plane, then you can consider the strike could be something like that, and this is the dip. Now the fold axis is like this. So the pitch of the fold axis with the strike of this bed is at high angle, and therefore we term it as reclined fold. The overturned fold is something that has both limbs dipping in the same direction. So this one you see is dipping this direction, and this one is also dipping in a same direction but with different dip angle. You can also see them in the stereo nets, and stereo nets are the best way to visualize if you plot the axial planes in the stereo net, and you can clearly identify whether your fold is upright, recumbent, inclined, reclined or overturned together with the fold axis. Just to come back, in this upright fold, this is the fold axis, here this is the fold axis, here this is the fold axis, here we have defined already this is the fold axis, and in this overturned fold, this one is the fold axis. Now for the first one, if we take the upright folds, clearly the axial plane is vertical, so the plot of the axial plane would be the red line. The fold axis, as you can see, this is horizontal, so it would come somewhere on the primitive circle. On the recumbent fold, it does not have any strike because it is a horizontal bed. So, the entire primitive circle is actually the plot of your axial plane, and the fold axis you can plot, if you can measure it, is somewhere here, and this is also horizontal. In the inclined fold, as we have seen here, it is dipping in this direction. So, it should be an inclined plane, that is why the plot is curved, not a straight line, and this is the fold axis. The reclined fold, as we talked about, that the axial plane here is also inclined. So, we see the great circle here as a curved circle, and the fold axis should be somewhere in the middle of this axial plane. In the overturned fold, we call this one as normal limb, which has the lowest dip amount. So, this is the normal limb, and then this one is the overturned limb. That means it got turned towards the normal limb and giving rise the same dip direction, but with different dip angle, and this is therefore overturned limb, and the axial plane should pass through the middle of this normal limb and overturned limbs. Now, all these things you have to see under, or all these things you have to see in profile sections, otherwise there could be some little error in plotting your data. Now, we will see how to classify the folds based on the plunge of the fold axis. And in this section, we have three different types of folds. One is horizontal fold, another is plunging fold, and third one is vertical fold. As the name suggests, a fold is horizontal if the fold axis is horizontal, that means it does not have any plunge, so plunge is close to 0. A vertical fold, I am taking the third one after that, is where the fold axis is vertical or it is close to 90 degrees, and anything between horizontal and vertical fold is known as plunging fold, or a fold whose fold axis is inclined. As you can see in this illustration here, this is a horizontal fold because the fold axis is horizontal here. This is a plunging fold because the fold axis has a plunge. If you consider this is your horizontal line on this plane, so this would be the plunge of this fold axis, and if you consider this one, the vertical one, then this is your fold axis, and of course the angle is quite high or close to vertical. So, therefore, we have, based on plunge of the fold axis, we have horizontal fold, plunging fold, and vertical fold. In some textbooks, these plunging folds are also classified in so many different categories based on 0 to 10, 10 to 20, and so on. So, highly plunging, moderately plunging, gently plunging, and so on. We are not going into that part, but anything in between horizontal to vertical is plunging fold. This is what we are going to consider for the lecture. Now, we are going to take over that on the fold axis, but whether now we are going to see if the fold axis is straight or curved. So far, all these illustrations we have seen the fold axis was straight. Now, if the fold axis is straight, then we call it cylindrical fold, or in other words, the way we defined the fold axis in the previous lecture, a fold which can be generated by moving a line parallel to itself, and this line, this particular line is your fold axis, and if you can do that, the produced fold, the fold you will produce out of it is a cylindrical fold, because the fold axis, the direction of the fold axis is not changing in this case. So, a cylindrical fold therefore has a rectilinear hinge line parallel to the fold axis, and if the fold axis does not have a straight hinge line or straight fold axis, then this is non-cylindrical fold. So, a fold which cannot be generated by moving a line parallel to itself, and the hinge line is either curved or the fold is conical. here is one example of cylindrical fold. We are a little bit bored now, but seeing the similar image or similar illustration. So, here we see we are particularly focused on the orientation of the fold axis. So, this dotted black line is the fold axis here, and you see the orientation of this black line does not change. So, it is straight, therefore, it is a cylindrical fold. However, in this case we see that the variation of fold axis, the orientation is changing along the hinge line and the hinge line as well. So, this is a non-cylindrical fold. Here you can have a line, and with this line if you place it, you can produce the fold completely. But here if you have a line, you cannot produce the fold completely, because at this stage you will have some sort of gaps and so on. This is also a different kind of non-cylindrical fold. So, here we have the depression along the hinge line, and here the entire hinge line is folded in a different direction. But the bottom line is that fold axis here is also not straight, it is curved, and therefore, this is also a type of non-cylindrical fold. Now, we will see how we can classify the folds based on the curvature of the axial planes. Again, so far all these illustrations we have defined axial planes or axial surfaces, all of them were straight, and this time we are going to see if the axial planes could be curved or not. So, if the axial plane is straight or axial surface is planar, then we term it as plane fold, and if the axial surfaces are curved, then we term it as non-plane fold. And here are 4 illustrations for you. The first 2 are examples of plane folds. So, and it is not a function, as I have drawn these 2 illustrations to convey the message that orientation of the fold axis not necessarily indicate or not necessarily justify whether the fold would be plane fold or non-plane fold. So, here we see, we have learnt in the previous slide, this is a cylindrical fold and this one is a non-cylindrical fold. In both cases, the axial surface or axial plane is straight, this blue plane. So, these are therefore plane fold, and it is indifferent whether the fold axis is straight or curved, or in other words, whether the fold is cylindrical or non-cylindrical. The same logic applies to the non-plane fold. The fold could be cylindrical or non-cylindrical in producing non-plane fold. What we see here, that here the fold axis, we have seen it in the last slide. So, this is your fold axis which is curved, the axial plane is also curved. So, this is a non-plane fold, but here the fold axis, you can see it here, you can see it here, or even here, these are straight, but axial plane, as you can see here, this blue plane which is dividing the fold or bisecting the fold curvature here is curved as well. So, here it is curved, here it is curved, therefore, both are examples of non-plane fold. However, in this case the fold axis is not straight, here fold axis is straight. So, we learned that plane fold and non-plane fold is simply defined by whether the axial surface is planar or curved. It does not have any relation with the orientation of the fold axis or whether the fold is cylindrical or non-cylindrical. However, we will use this plane fold, non-plane fold, cylindrical fold and non-cylindrical fold when we learn more the superposition of deformation, and we will see and come back to all these kind of illustrations. So, I request you to understand this part very, very clearly. Now, based on interleave angle, we classify the folds as gentle fold, open fold, closed fold, tight fold, isoclinal fold and fan fold. It's essentially based on, or the difference or the classification is based on that how much the interlimb angle is. If interlimb angle is from 80 degrees to 120 degrees, then it is gentle fold. If it is between 120 degrees to 70 degrees, then it is open fold. We assign a fold as a closed fold if the interlimb angle is between 70 degrees to 30 degrees. A tight fold is where the interlimb angle is 30 degrees to 0 degrees or sub-zero. The isoclinal fold is where you cannot define an interlimb angle. That means the two limbs are subparallel to each other. And then fan fold is something where we have negative interlimb angle. So, this is an illustration. You hardly see this kind of folds in a single layer, but this I have drawn to sort of accommodate all these classified folds under interlimb angle. So, this is a fan fold. As you can see that here and here the interlimb angle you cannot measure in this side. This is therefore a negative interlimb angle, and we call it a fan fold. In some texts, fan folds are also given a term called elastica. If you hear it, then you just remember that it is related to fan fold, but elastica is something completely different in terms of waves and other descriptions. So, we are not going into that part, but fan fold sometimes you can see in some textbooks that are termed as elastica. Now, of course, this is a gentle fold, this one, the interlimb angle is pretty wide. This is an open fold, this is a closed fold, this one is a tight fold, and here you see the two limbs are running almost parallel to each other, and therefore, this is an isoclinal fold. So, this is how we define folds based on their interlimb angle: gentle fold, open fold, closed fold, tight fold, and isoclinal fold together with fan fold. Now, shape of the hinge is also one of the very important parameters to describe folded structure, and here I have shown only 4 end members you can think of. So, these are kink fold, chevron fold, concentric fold, and box fold. What we see here that this kink fold and chevron fold, both of them have sharp hinge like this, and in terms of fold geometries that we have learned in the previous lecture, let us have this profile or this line. We try to do it. You see, when you encounter a chevron fold in the field, it is very difficult or it is impossible to define the inflection point, right. So, it is somewhere here, right, but the sense of curvature actually is changing at the hinge points. So, this point you do not change the sense of curvature. So, typically this cannot be inflection points, and this is why I am repeating the fact that these terminologies that we use to define the geometry of the fold are very much qualitative, and they vary from one kind of geometries to another kind of geometries. So, keep this always in your mind that not necessarily in each type of folds or each type of geometry you can define each and every terminologies that we are learning so far. The concentric fold is something like this, where along this point the folds do generate. Here along this point you can see the folds have generated. That means it has some sort of a center. Along this center the folds are generating. This is known as concentric fold, and if so, here we see this in multi-layer, but sometimes we call it cuspate lobate fold as well. So, cusps and lobes, these are forming alternatively in this kind of folds. Now, box fold or double hinged fold is something like this, where we have seen it before. We have in one segment of the fold we have two hinge points, and therefore the axial trace, you can see here, they are some sort of converging towards the fold core, and these are known as box folds. And sometimes we see this kind of folds when we deform the thin multi layers of contrasting competence contrast. So, based on the shape of the fold hinge, we define it as king fold, or we just say king fold, chevron fold, concentric fold and box fold, and they are mostly identified or they are classified based on their appearance and the geometry of the hinge. Now, we are on the last part of this classification, which is geometric relations with the neighboring structures. And here we learn a series of terminologies as well to define how one folded layer or a stack of folded layer is related to the neighboring features. And the first one we will take over is harmonic and then disharmonic folds. Now, folds in which axial planes are continuous across successive folded layers that show approximately the same wavelength and amplitude are called harmonic folds. So, as you can see here in this part on the left side of this illustration, you can connect the axial trace of all these successive layers. Okay. Here you can also connect all these successive layers. So, these are your axial traces. Okay. So, when that happens, that these folds are in a harmony, these are known as harmonic folds. However, in contrary, folds in which the amplitude, wavelength and style of these folded layers do change along discontinuous axial surfaces from one layer to another are disharmonic folds, as you can see here on the right side of this illustration. You cannot connect. So, you can connect these three, but then it is here. So, there is a discontinuity, there is a disharmony. Here, for example, you see an antiform, and if you try to connect it, you arrive to a synform. So, here all these things are little jumbled up, and therefore, they do not have any harmony in these folded layers, and we call them therefore disharmonic fold. So, we learnt what is harmonic and what is disharmonic fold. Now, harmonic and disharmonic folds also related to some sort of ordering of the fold. As you can see here, if I consider this, that this is some sort of what we learnt there, that Z fold, M fold, S fold and so on, clockwise local vergence, anti-clockwise local vergence and so on. Here you also develop this W folds and so on. Now, what is the message I will try to convey here, that you can have a large fold like this, and then this large fold may be defined something like that, and then this small folds also can be defined by smaller folds and so on. So, the red one we call it first order fold. The green one is the second order, I write it this way for better space, and the blue one is third order fold. And this first order, second order, third order and so on, these folds can be of harmony or can be of disharmony. This is how they appear, but this is where in this slide we learn the orders of the fold. So, large fold wavelengths are generally lower order and small wavelengths are generally of higher orders of folds. Okay. Then there is something called periodic and non-periodic folds. Now, if within a train of fold you have series of synforms and antiforms and so on, so with more or less same geometry between alternate points of inflection, if you see that, then this is known as periodic fold, or in other words the folds look very similar, they are similar to each other. So, one set of fold here, the next set of fold here, and they appear in a very similar way, and these are known as periodic fold, that is the same structure appears periodically. And if that does not happen, that they have a dissimilar geometry, then this is non-periodic fold. So, as you can see here in a very rough sketch, that this structure is appearing here as well, appearing here as well, here as well, and therefore, this particular structure is getting a periodicity in the next structure. However, in this one we do not see this. So, first one is like this, second one is something like that, third one is like this, and so on. So, this is a non-periodic fold. Now, non-periodic folds, there is a special kind of non-periodic fold which is known as polyclinal fold. What we see here in all these cases, I use this typical color for axial planes. The trace of axial planes does not matter whether the fold is periodic or non-periodic, the trace of axial planes are more or less constant, right. But in polyclinal folds, you may have folds like this, or you may also have folds like this. This is not very common, where you see that in the first case the axial planes are converging towards the core, and here axial planes are converging away from the core. So, these are known as polyclinal fold, where axial planes in successive layers are different to each other, the orientation of the axial planes to be specific. Now, then there is another type of folds which is known as anéchelle fold or anéchelon fold. This is a French word, I do not know how to pronounce it properly, but most likely anéchelle fold. So, it is a very special type of folds in some non-cylindrically folded surfaces or doubly plunging and relatively short, nearly upright folds. In you see in a parallel series, they have alternating antiform and synform axis oblique to the fold string, and these folds are stepped and consistently overlapping to each other, and they define an anéchelle array of folds and known as anéchelle fold. So, this is an illustration as you can see here. So, if you have some sort of a ductile layer on the top, this yellow one, so this is little ductile, and if you have a strong layer which is brittle, and if you generate a fault, a strike slip fault, we will learn it soon in the one of the next lectures when we talk about fault. So, if this block slips the other block, then it drags the top ductile layer, and when that happens, then you form series of folds in an array, and these folds together known as anéchelle folds. Now, there is also another important terminology related to the geometric relations with neighboring structures, and this is called décollement or décollement. A décollement is a process which gives rise to a train of folds in a layer which becomes detached from the adjacent layer either at the bottom or at the top. So, the adjacent layer therefore does not suffer or enjoy any deformation. So, it is almost unfolded or undeformed. And this kind of décollement or this kind of features you generally see in large scale orogenies. So, what we see here, this series of layers, these are getting folded. So, it got folded like this. However, here, so here is the fold, it got detached from this surface. So, this is the opening due to detachment, and this is kind of slip surface, and this is known as décollement or décollement surface. And I repeat, these things you hardly see in small scale features, but you mostly see these kind of features when you go to or when you map a large scale structures, then you see this kind of décollements. The final one we will see is called intrafolial fold. So, folia means leaves. So, intrafolial means a fold between the leaves, or in our case a fold between some layers or fine layers. So, this is defined as an isolated asymmetric tight or isoclinal fold sandwiched between apparently unfolded foliation surfaces. Usually the apparently unfolded layer forms the limbs of the larger folds. When intrafolial folds occur as tectonic inclusions, they are described as rootless intrafolial folds, or we simply define it as rootless fold. And in this context there are few other type of folds. So, we generally term them as subsidiary folds like minor folds, drag folds, parasitic folds, etc., etc. These are kind of smaller folds and they occur over a large fold with subparallel hinge lines. So, let us look at the intrafolial fold here. So, you see you have strata with apparently no deformation, at least in this section, and in between you have a layer which is strongly asymmetric, very tight fold in between, or which is sandwiched between almost virtually undeformed layers, at least in this section, and these are known as intrafolial folds within finely laminated layers. So, with this I conclude this lecture. In the next lecture we will first learn a very special type of fold classification is given by Professor Ramsey. It is called deep isogons, and then we study the different mechanisms of folding processes, that is how the folds do form differently in different tectonic settings and so on. Thank you very much. See you in the next lecture.